All right, let's get started. So we're going to cover a device today that most of you all are probably pretty comfortable with and have a a reasonable familiarity. You see them everywhere. You probably have multiple versions in your house. And if you're ECE, most likely, if you're going to build something that has a power supply, it's often better to take a transformer and just step it down. And why do we do that? Because of that third bullet right there, the ability to inexpensively, maybe we can even use another word, cheap, right? Cheaply change voltage levels from a higher level to a lower level or vice versa, right? It can go bi-directionally, although there is some challenges and we'll talk a little bit more about it. But over the summer, I went to a conference and they're talking about this bi-directionality. Some of the transformer manufacturers may not necessarily be designing them so that they are truly bi-directional. But for our intents and purposes in our class, we'll focus on them being bi-directional, the power devices. So you can work up to 765 kV or down to 120 or even lower. You know, it really depends on what you want. If anybody here has an older dole rail system, you don't have the ring stuff, right? If you have the old push button, you hear the ding dong, and it's not wireless. If it's hardwired, you most likely have a very small transformer that steps that house voltage down to around 24 volts AC is typically. But going into our house, there's a transformer with 100% certainty. There's a transformer that steps it down to 240 volts, at least here in North America. And then we have the 120 again for the center tap. So we'll look at that in more detail. Transfers various power levels. Notice I said power levels. Is that the right term? The power isn't transformed because I don't take power from a higher level to a lower level. I take the voltage from a higher level to a lower level. And conversely, the current is the reciprocal of that. It would go from a lower level to a high level. So a transformer is essentially a constant power device, meaning all the power that goes into the transformer, almost all of it comes out of the transformer. Very, very highly efficient devices, 99% efficient at full load, not a lot of losses. And so, like I said, oftentimes we'll assume that they're 100% efficient to kind of make our work a little bit easier. And then the problem with transformers is it's a physical device. It's got a set of windings. It's got iron in the core. It also may have some oil, or it could be a dry type insulation, which would be an epoxy. It's a pretty complicated piece of equipment. Yes, sir.
For isolation?
Absolutely. Anybody know what we're talking about when we talk about isolation? Why is it that we all interconnect to the grid that comes on the pole at 7,200 volts? And why do you never worry about touching something that could be 7,200 volts in your house? Faults occur all the time, right? Piece of equipment, a wire could go across and cause issues. Why don't you ever get 7,200 volts in your house? It's because of electrical isolation. The path on one side of the transformer, the back and forth, right? Because we have to have a closed loop for current flow, is 100% electrically isolated from the other side. So if you were going to have a fault to ground at 7,200 volts, the return path on the other side is distinct from what you would have in your house. So it's not like you would touch the 7,200 and touch a wire in your house and you get electrocuted. You shouldn't get electrocuted. If you touch ground, it would be a different story, but that's the return path for it. So that's the primary reason why we use transformers for utility perspective. Obviously, it steps down the voltage to much more manageable levels, but we don't want 7,200 volts going into our house. Nothing anywhere close to that. The other thing about it too, remember how we talked about three-phase systems? Well, in reality, we have three-phase transformers, but there are not really three-phase transformers. There are three single-phase transformers that we will connect in delta or Y to go ahead and make a three-phase total transformer, okay? Now, you can buy those in one complete package. So you see three bushings and the three individual phases are interconnected inside the transformer. But those are for smaller transformers. If you get to really big transformers, like pushing 800 MVA in size, those usually can't be three-phase transformers. Anybody want to guess as to why? No, not interference. Just too big. You got to ship these over the road, and the transformer, even if it's dry with the iron, it would weigh too much for most roadways. So you wouldn't be allowed legally on the roads. So 750, 800 MVA, if you're pushing that size, you almost always will have single phase transformers. That would be a third of the full nameplate rating. And then you would go ahead and do there. Also, I went to Clemson, South Carolina, where Clemson University is, and looked at their electrical distribution system. And I think they had 10 MVA transformers, and they had single phase ones. And the reason why they had single phase ones is because if one transformer failed, you could just plug in another one. You know, they had a spare one on campus so that they could maintain the reliability of the system. Because a college campus, right, there's 10,000, 15,000 people living on college campus. It's pretty darn important to maintain electricity. How much of a humanitarian issue would happen is if power on campus was lost for a day. You know, if they kick you out of the building so all the ventilation doesn't work, you wouldn't have heat, so they'd send you to the rec center, and they've got backup generators to take care of ventilation and emergency lighting and that type of stuff. So you got to make sure that that power is reliable. So on campus here, we're fairly reliable. We have 2 incoming connections on campus that are somewhat distinct from each other. But that, you know, kind of is low potatoes. If you get more important, like ESRB has a backup generator. It used to start every, I don't know, Wednesday at 8 o'clock or 9 o'clock in the morning. And I don't know what time it starts now, but that's right outside Barrows. And so what they've done is they've just put backup generators all around campus to kind of do that. If you're a more organized way of doing it, like at the hospital down at Northern Lights in Bangor, they have a backup gas turbine that they can run power completely independently from the grid. So they have a lot more redundancy, plus and then the hospital can run. Yes, sir.
I understand that everything is spread on transformer, but how likely is it for transformer to fail?
So the question is, how likely is the transformer to fail? So there's always, it depends, right? And one of the depends things is one of the biggest enemies for electrical systems is heat. So if you have a transformer, and I know about this because again, this is a project I worked on many years ago. So I was in Mount Olive, I think it's North Carolina, and it was one of the largest turkey processing facilities in the world. And they had this electrical room that they were always burning out transformers. And they asked me why, you know, why are they burning out? So I walked in the room and it must have been 120 degrees. And it's like, it's too hot in here. You walk in and it's 20 degrees over the ambient for what the temperature is designed to operate at. And so it's just heat. So transformers that aren't maintained in a good environment, temperature usually is a problem. Most of the transformers you all will come across are oil filled. They're permanently sealed transformers. So like their pad mounts located across campus, those there's no maintenance. They're designed to have no maintenance. But bigger transformers that have a lot of power and a lot of changes, they have to be tested and they have to be maintained. Sometimes you have to change out the oil. So you run tests on those every year to every 5 years. And if those tests are run fairly regularly, usually a transformer will last you 20 to 40 years. No moving parts, right? So that makes it pretty effortless. You do have some transformers that have fans on them for cooling, but that's just external. If it gets too hot, they'll trip the transformer offline to protect it. So yeah, transformers, extremely, extremely reliable. Probably the most reliable electrical equipment, you know, that actually does something in the world. Again, no moving parts. Come on. So we'll start off with an ideal transformer because that's the easiest one to start with, right? And the ideal transformer has no real power losses. All of you have taken physics 1 and 2. So when I talk about infinite permeability, what does that mean? I can really pick on the ECE students, right? Because they've all taken EMAGs. That was a big hint of the answer. What is infinite permeability?
Permeability is the ability for something to conduct magnetic field, right?
Yeah, it's basically a way of determining or measuring how good of a magnetic conductor something is. So if you've been paying attention in the news over the summer about tariffs and some of the things that China has perhaps been trying to do. And again, I'm just saying perhaps, I don't know if this is true or not, but limiting rare earth metals. Yeah, everybody know what those are? Those are really fancy magnets that have very high permeability. And if we don't have access to those, all these devices that rely on magnetic fields, small motors for the most part, but maybe even transformers, they have to get bigger in size and they're less efficient. And so you can't produce as efficient a vehicle or whatever using different rare earth magnets. And does anybody know what like the best permeability is out there for magnetic material? It's about 200,000 times better than air, which is pretty good. But think about electricity. How much better of a conductor is copper compared to air? About 3 million times. So it's an order of magnitude better, which is a good thing, right? Because anybody here has got their cell phone and their wireless computer. That's all transmitting over the air, right? It's all a magnetic signal that is being transferred back and forth to wherever the receivers are. Are we all sitting here getting electrical shocks the whole time? No, because the air is a really good electrical insulator, but it's an okay magnetic conductor. And so the way that we compare those two is called permeability. If you're familiar with the term conductance for electrical circuits, that's what the analogy is. If something has got a really good conductance, right, it has a high number. So copper has a good conductance. Its conductance would be 3 million or something like that, where permeability would have a good conductor would be like 200,000. Okay. And so there's a lot of work in improving permeability because, again, if you can get more magnetic field through a device with less effort, you can make it smaller and more efficient. No leakage flux, as we just talked about, right? Air is a pretty good conductor for magnetic energy. So magnetic field that is you're trying to stay in your transformer can easily leak out into the air. And so you're designing these transformers to limit that as much as practical. So in our ideal transformer, we'll say none leaks out. All the flux that we send into the, or that's created inside the transformer is going to be essentially linked by the other winding. Now, this is a definition, and a lot of people screw this up. It's the primary side is usually the one that takes the power. And the secondary side is the one that usually delivers the power. Normally, when you say primary side, you say high voltage side, right? Because like at our house or even in this building, the high voltage comes in at 4160, and then it steps it down on the secondary side, steps it down to 208. But that's not always the case. Think of a generator step-up transformer. The generator generates at like 22,000 volts and immediately takes that voltage and steps it up to maybe 345 kV and sends the power to the grid. So primary is the power goes in, and secondary is the side that it comes out of, all right? So don't get confused. A good friend of mine works for a company, and he's always talking about he's the primary guy, which he implies it's high voltage. And he's a transformer guy too, and I say that's actually incorrect. But he says, well, I'm just gonna call myself the primary guy, so it is what it is. A little bit of magnetic field stuff. So we got a shell of a transformer here. So we have some sort of magnetic material. That's the core of the transformer. And again, that's got very good magnetic permeability. So it's a very good conductor for magnetic energy. We're going to wrap a wire that's carrying current around that magnetic core. And we're going to run a current through there. And so we know that when we run current, run a core, we just run current in a wire, we're going to generate magnetic flux surrounding that wire. But that magnetic flux is all going to stay inside the transformer, okay? Every last bit of it stays inside the transformer. Now, because it's a good conductor for magnetic energy, we're going to get the flux that flows around in a loop. So just like current in a circuit, your flux has to flow around in a loop. It has to kind of return back to where it came from. In the secondary side, we have a transformer winding that, again, wraps around that core. And now you get a flux going through that core. And if that flux changes, it's going to induce a voltage, or it's going to induce a current, which will thereby induce a voltage. Okay. So a bunch of things need to happen here. We have to have a magnetic core that has the flux that flows through it. It has to be wrapped around it. No flux can be leaking if it's ideal. But I said one key thing. I said the flux has to be changing, right? If you don't have a changing flux, eventually what happens to an inductor that's fully charged? It becomes a short circuit, right? Because it's not generating any opposing magnetic field. So it's not generating any voltage. So if I take a transformer and I connect it to DC, what happens? It would short out, wouldn't it? You don't have d phi dt, which is the flux, is zero. So you would not have an actual load. So now you can see why Edison was not going to be able to go forward, because transformers only work on AC current or AC, because I don't want to say alternating current. It only works on AC. It cannot work on DC. You can do some tests on transformers using DC, but that's because you're trying to do very specific testing. You're not operating a transformer at DC. So be mindful when everybody says, hey, take this transformer and plug it into your 5-volt DC source and get 10 volts out. I've had senior project groups come to me and wonder why the fuse kept popping. So don't be that group that does that, because we have a good laugh, but it's also frustrating for you because you all can't figure it out. So here are some equations. We have our flux and our flux linkage. Excuse me, I think I have allergies or a cold. I'm not sure which. So N is the number of turns of the winding, and then phi is the magnetic flux. So the flux linkage is going to be equal to N times phi sub N. And the same thing for flux, the flux linkages in number 2. But now we use N2, which is a turns on winding number 2. But the phi sub M is exactly the same value, right? Because it's a series circuit and we don't have any leakage flux. So all the phi sub M on one winding is seen on the other winding. We get our voltages by taking the derivative of the flux linkages with respect to time. And we do that for both primary winding 1 and primary winding 2. And then we see that d phi m dt is the same for both the primary and the secondary, or winding 1 and winding 2. We set those equal to each other, and we end up with something called the turns ratio, which is literally just the number of turns on winding 1 divided by the number of turns on winding 2. Okay? We just divide those two. Now, it's also equal to the primary to secondary voltage ratings. Those are the same things. And in fact, it's a lot more useful to talk about turns ratio as voltages, because when I buy a transformer, and if I'm told the turns ratio is 1,000, can I plug that transformer into my outlet over here? Maybe I can, maybe I can't. What if the windings were rated for like 5 millivolts and 50 millivolts? Plugging that in to my outlet would burn up the transformer because the insulation couldn't handle it. So knowing the turns ratio as a voltage, which is 7,200 to 240, means I still get the turns ratio correct. I get 60, right? But I also know what that transformer is nominally rated for, so what voltages I can apply it to. So nobody ever talks about the turns ratio as 1,000 or 60. They always talk about it from 7,200 to 240. So every transformer you buy, even if you buy one for your senior project, it's going to be 120 to 5 volts or something like that. Okay, that's the typical way that you'll talk about it. So let's do a little bit of current, because we want to go ahead. Go ahead.
Will the temperature change if the transformer is used in reverse?
It does not change.
Because the primary is now the secondary. Secondary is not primary.
Right, but it's still the same basic design, right? It still has the same number of windings. It still has all that same stuff. So the way that you get a higher or lower voltage is you just change the number of turns on the winding. So in the lower winding, you have more current going through, right? The lower voltage winding, you have more current, but you also have bigger conductors. So your I squared R losses should be about the same. Make sense?
the bottom sector is V primary over V secondary, right?
That's the actual turns ratio. Yep.
Now, the V primary, let's say, is 200 volts. The
Yep.
secondary, you have 12 volts.
Yes.
Now, if let's say you want to use it as
12
1 volt on primary and then 220 on the secondary, will it?
Oh, you can't switch the voltages around. Because you're trying to plug a winding that's rated for 12 volts, you plug it in with 220, the insulation of the windings may not be sufficient. Right? So you can't just swap it around and do that. The other thing too is that you actually use bigger wires or bigger copper conductors on the secondary side, the low voltage winding, than on the high voltage winding because you get more current flow. So you don't run the same size conductor, you run smaller because everything is trying to be built cheaper, right? If I can get something that's going to have 1/3 the current, I'm not going to run the same wires because it's going to be a lot cheaper for me to run smaller wires on that lower voltage winding. So to do the current, you have something called the magnetomotive flux, which is proportional to or equivalent to voltages in a circuit. And it's going to be H dotted into the differential length. H is the magnetic field intensity. The integral sign with a circle around it, for those of you who took vector calculus, that's a surface integral. If you remember it from, everybody's like, oh no, we won't do any vector calculus. You don't have to do that here. We're going to go ahead and assume everything is neat and orderly. But that's going to end up being N1 times I1 plus N2 times I2. And then our MMF, if we make everything neat and orderly, we have just the magnetic field intensity times the length. And you can get the magnetic field intensity from the flux density multiplied by that length. And then the mu term is the permeability of the material that you have there. If the flux density is uniform, so just like in a current carrying wire, you have a current density and you assume it's uniform throughout the device. We're going to have the same thing here, that the flux density is going to be uniform. So it makes our work even easier, which means now it's just the flux times the length divided by the permeability times the area. If my permeability is infinite, then it just becomes 0, right? On the left-hand side becomes 0. And I have N1 and N1 I1 plus N2 I2. And then I solve, and you'll notice I1 and I2 are equal to the opposite of the turns ratio we had for voltages, right? V1 over V2 was N1 over N2. Now I1 over I2 is N2 over N1. Does that make sense? Is that right? As my voltage goes down, this is saying my current goes up. As the voltage goes up, the current goes down. Is that what you expected to?
The same.
Yeah, if the voltage goes up, the current has to go down by the same amount if for the power to be the same, right? If I'm plugging in 10 megawatts here and I'm stepping the voltage up by a factor of 10, that current better go down by that same factor to make sure that I get around 10 megawatts coming out. And in an ideal transformer, it'd be exactly 10 megawatts. So they have to be the inverse of each other to maintain that constant power. If the voltage and the current went up, that would tell you that now I'm getting more power out and I can't get power out of nothing. So I would have to get the power from someplace else. In a transformer that doesn't exist, you can have an additional set of windings on there to get more power through there. But for the most part, most transformers tend to be just 2-winding transformers. I've seen a couple 3-winding, but 2-winding are by far more common. And so what we have on the lower right is our equivalent circuit for an ideal transformer. This is what we model when we do circuit analysis for a system with a transformer. It has nothing to it. It basically has a device that is going to take the voltage or the current and step it up or down correspondingly. And the correspondingly is based on N1 over N2 or V1 over V2, depending on which way you look at it. This is probably the only new, if you haven't seen transformer modeling, this is probably the only new electrical device that you'll see that you need to be able to model systems. Because if you think about it, all the electrical circuits you've done so far, you got a power supply, you got a resistor, you've got an inductor, and you got a capacitor. Is there anything else that you've added in your bucket of tools for circuit analysis? Op amps? Can I build an op amp and just, isn't it a bunch of resistors and multipliers and all that stuff? But a transistor, I can model a transistor as a dependent source with some resistors on it too, right? If you look at the equivalent circuit. So this is the only one. This is the equivalent to what we'd call a gain block in electronic circuits. But this is just for AC circuits. So we actually need to add this one circuit element to make our system work. Okay, if you can do base bones, root circuit analysis, you would have the transformer there. This turns ratio can be a purely real number, or it can be a complex number. And we'll see how we connect transformers. We actually can introduce phase shift across a transformer. So what you may see is you might see an E to the J theta thrown in there to indicate that you're going to get a phase shift from one side to the other. Okay. But for the most part, you don't need to worry too much about phase shifts. Through transformers, we can oftentimes neglect them. Well, how do you reflect impedance through a transformer? Because when we have a transformer and we have a circuit, and I'll just show a single line diagram, connected to a generator, and here's my load, I want to calculate what the current is flowing out of there. But if this load is a 3 ohm load, I've got to reflect that resistor through the transformer. How do I do that? Well, here's what I've got. And what I want is this. Okay, I don't want a transformer in there. So what you need to do is you need to reflect V2 to this side and I2 to this side. Do you remember how we did that? Well, we know we have a turns ratio, which is V1 over V2, or it's equal to I2 over I1, right? Everybody see that so far? So my current I1 over here is going to be equal to, let's see, that's going to be equal to I2 over A. That's my current. And my voltage over here, V1, is going to be equal to V2 times A, right? Just by using my turns ratio. So now my R equivalent is V1 divided by I1, right? Which is equal to V2 times A divided by I2 divided by A. Everybody see what I've done there? I'm just taking the parameters or the voltages and current that were on the secondary side of the transformer, the V2 and the I2. I reflected them to the high side of the transformer, V1 and I1, by using the turns ratios. And then I know the equivalent load is whatever, and I take V1 divided by I1, that's our equivalent. That's equal to A squared. So V2 divided by I2 is R2 times A squared. So if you have to reflect impedances across a transformer, you have to use the square of the turns ratio. Okay? Gotta reflect the impedances using the square of the turns ratio. Not the turns ratio, but the square of the turns ratio. All right? Pretty important that we reflect it that way. So now let's look at a real world equivalent transformer. So real transformers have losses and leakage flux, and you do not have infinite permeability of the magnetic core. So where do the losses come from? Well, you've got I squared R losses because you've got a piece of copper and you've got current flowing through the copper. So you got I squared R losses there. And you have losses on both the primary and secondary windings. Anybody know what eddy currents and hysteresis are? Do you all know what eddy currents are? For those of you who don't, eddy current is if you have a magnetic field and you have a piece of metal that's within a magnetic field, that magnetic field is going to be changing and it's going to be seen inside that metal piece. And so what happens is it induces current, right? You've got a changing magnetic field, and as long as you can link that flux, you're going to induce a current in there. And so those eddy currents are like the water eddies that you have, like water, flowing in a river, and it kind of goes around and it just circulates. It doesn't really do anything. It's the same thing for currents that float in the core of the transformer. You've got magnetic fields that are changing, that are inducing currents in the core of a transformer. Eddy currents tend to be pretty low, so oftentimes you can ignore them, but sometimes you can't. Anybody ever look at a transformer and see how a transformer is built?
Metal?
They call it laminations. Yeah. Anybody know what? Oh, I should also say sometimes when the computer brings up like I had some news. I have no knowledge. I just bring up Edge, and that's whatever MSN has determined is appropriate for plotting. So I'm not, whatever was on there, I didn't even know, but I'm not any political affiliation. I don't know what happened. So if anything is on there that offends somebody, I apologize. There is no intention. I literally just started Edge and it just popped up with, I don't know, whatever it was. I saw president on there. So I don't mean to offend anybody with stuff like that. So I can't always say that sometimes images are going to pop up and they might be offensive, but I can assure you that is not intentional. All right, let's see if we can look at this transformer here, which is a pretty cheapy transformer. And here's the core of the transformer. Do you notice it's a bunch of thin pieces of metals? You can see, little sort of pieces of separation where the metal, those are just thin little pieces of iron or some magnetically conductive material. And what they do is they just put a screw through them in the four corners, and then they cinch that screw down and it keeps it tight. But what you don't know is there's a little tiny bit of epoxy, just like in magnet wire. Anybody here had magnet wire? It's like that purplish wire. There's a thin layer of epoxy that acts as an insulator. The reason why they put the epoxy between the laminations is epoxy is a really good electrical insulator, but it's not a very good magnetic insulator. So the transformer has almost no eddy currents because it's a little tiny thin sliver of metal where the current can flow, and it doesn't really affect the magnetic energy at all. So every transformer that you'll find, every motor that you'll find, almost any device that uses magnetics will almost always have some sort of laminations to reduce eddy currents. And again, this is I didn't even know the size of this one. It doesn't say on this side, but 250 VA, right? I mean, that's less than your hair dryer takes, right? So this is a pretty small transformer. And so that's a cheapy transformer. And then that's what they have. So all transformers come with laminations because it's pretty cheap. So that reduces our eddy currents. And you can see the little bit of discussion here. There is some hysteresis effects, which is a memorization feature, but those are so small that we don't even really ignore them. But it just, whenever you magnetize something and you take the magnetic field away, it tends to stay magnetized unless you heat it up or sometimes you drop it. That's why you have permanent magnets. And if you get them enough to high enough temperatures, they'll lose their magnetic remembrance. If you drop them, sometimes that'll shake things loose. Well, you'll get so that you won't have all the norths and the souths lined up. This is a hysteresis curve. So if we include the fact that we're going to have some leakage, now our flux linkages has a leakage component here. You can see we added those two elements over here. And then when we calculate our voltages, we have the leakage inductance, the stuff that goes out in the air, plus we also have some I squared R losses, right? Or basically voltage drops across those coil. So how do we handle that? Well, before we can actually handle that, we need to include also the effect of the lack of magnetic permeability. So we have an MMF that has to drive the magnetic field around, and that's essentially lost energy, not lost energy, but lost magnetic field that doesn't do anything. So this term is the reluctance of the core. Since it's not zero, there is some reluctance, and our difference has to make up for that. So that's our magnetizing current, which is this value here, or we can write it as that. So normally our transformer has a pretty decent size, not huge, but a pretty decent size inductor that is responsible for the leakage losses or the magnetizing that's associated with the core. So here's our final transformer. This is the whole kit and caboodle. That's not ideal. We have our ideal transformer here. That's that new device that we're talking about. We have I squared R losses in the primary. I squared R losses, I'll put IP squared R. I squared R in the secondary. We have, this is just our leakage on the primary. And this is our leakage on the secondary. This is my eddy current loss. And that's my magnetizing energy that I need to magnetize the core. Okay. Normally, we take these two and dump them into those two. So we end up with an equivalent circuit that has just the two. In real world power systems, almost always that's enough. Because again, in quality built transformers, R sub C and XM tend to be pretty low. Okay. So here's our simplified equivalent with our core and our magnetizer. Questions on the equivalent circuit model for a real world transformer? No questions? All right, so how do you find out, right? So we have a transformer and we have to figure out how we're going to solve for all these parameters. Well, you all are smart engineers. How would you solve for RE and JXE? You can't go put a multimeter on it because the leakage flux is determined based on, what's happening with the machine or how much the transformer, how much energy is being leaked out. You also have I squared R losses that you have to be able to measure. You can certainly measure the copper resistance, but that's not usually all that accurate because now your magnetic fields are interfering with it. So how would you measure RE and JXE? What would you do? What I would do is if I made these so big as compared to these two, that I can ignore those two. I can neglect them without having any mistakes. So what would be an example of running this transformer so that I got fairly realistic numbers for a real world test? How about I run gobs and gobs of current through here? So I got pretty big losses there. But I want this voltage to be pretty darn low. Is there a case when you can get gobs of current when you apply a pretty low voltage? Short circuit. So if I short circuit the transformer, I'm going to get the full load rating of the current, the full load amps of the current for the transformer. And this voltage, excuse me, is maybe going to be 20% nominal. So I'm going to get big voltage drops across my RE and JXE and very little losses across here because I'm essentially going to have almost no voltage. And when you look over here and I reflect it through, you can even see that's pretty low. So the short circuit test, or sometimes the full load test, is going to give me RE and JXE. All right. So how do you do a full load test? You set a dead short circuit on the secondary side. You have a variable AC power supply that you turn up until you're measuring rated current flowing into the winding. And it could be either on the primary side or the secondary side because they're going to be proportional to each other based on the turns ratio. And then you measure a bunch of parameters. What would you measure to be able to measure, to be able to obtain RE and JXE? So I'm putting a voltage here. And it's variable. What would you need to measure to be able to calculate RE and JXE? So my short circuit test, here's what I actually have left over. So what would you measure? Forget it's a transformer. I gave you a lab assignment, a homework assignment. Go ahead and tell me what you need to measure. You can go to the lab and do whatever you want. But inside of a box, I have RE and JXE. What would you do? What kind of a set of parameters would you measure? Would you stick a multimeter on it and measure RE and JXE? Hope not, because we just talked about the fact that you have leakages and you have I squared R losses, and those aren't going to be all that useful to measure that. So what would you do? If I measure the current and the voltage here, I can go V divided by I. What's that going to be equal to? Is it equal to Z? Which is Z? Yeah, RE plus JXE is equal to Z. Is that correct? No, not correct. What did I say when we left lab? What do we know about voltage and current? What do they have? Magnitude and angle. He's walking up with his fluke and he measures the magnitude of the voltage and the magnitude of the current. But the voltages have magnitudes and angles. So I've got to get these angles, right? Otherwise, if I just measure this, and all I have is this, right? So I have the magnitude of Z, but I don't know how much RE is, and I don't know how much JXE is either. So it's impossible for me to go ahead and measure that. So I'm going to have the angle. Well, the first thing I do is I'm going to define my applied voltage to be at an angle of 0. It's just a reference. I'm going to pick it. So this is going to be at an angle of 0. How do I get the angle of I?
90 degrees.
90 degrees?
Because only in battery, there's no capacitor.
But there's a resistor, right? The resistor and the inductor don't give you 90 degrees. So what is the angle associated with I? How would you get it? You're going to plug this into an oscilloscope? Oscilloscopes only measure voltages, right? They don't measure voltages and currents. And you're going to buy an oscilloscope that can measure 345,000 volts. You all have that in the EC lab upstairs? You do? Can I borrow it?
Yeah.
What are those good for? 20 volts? 50 volts? If you only had something that was rated for 50 volts, I would encourage you to leave it home because it's not going to do you much good in the power world, right? So what are you going to do? I wonder if there's another set of parameters that you can measure that would give you the angle of the current. In our last class, we did a lot of S equals VI conjugate, right? And if V is at an angle of 0 and I is at an angle of theta, we saw that we get P and Q, and that's the angle theta, isn't it? So I got to measure voltage and current magnitudes. And if I can also measure the power going in, I can build myself a power triangle. From there, I can get theta. Once I have that, then I can get RE plus JXE. So the short circuit and no load tests, the short circuit or full load test, you've got to measure three things: voltage, current, and power. And you're putting a short circuit on the output and you're slowly turning the voltage up. By the way, I can do this test on either the primary or the secondary. So the question is, should I run the test on the primary side or should I run it on the secondary side? Or let me back up. Should I run it on the high voltage side or should I run it on the low voltage side? One's going to have a short circuit. The other one's going to have the one with the power supply and all that stuff. Which one should you put the equipment on to do all your measurements and apply the voltages? The high voltage or the low voltage? Why?
Because the losses in the high voltage side would be a lot more.
They're the same. It all gets lumped together, right? So they get lumped inclusively. It's actually a very practical experience. So this short circuit over here is going to be, let's say it's 2000 amps. And I run a very short wire between the bushings, right, to make it 2000 amps. Over here, maybe I need 200 amps. But now I've got a whole test rig set up where I've got to run cables and all that stuff. So is it easier to get wires that are running at 200 amps or 2000 amps? Way easier. Most of you don't realize because you've been doing stuff, in a paper environment. But when you calculate something and you got to run 2000 amps of current, you're running multiple 1-inch diameter cables per phase. You're running like 5 or 6 cables per phase. That's a lot of copper. That's a lot of money. Where 200 amps, you could probably get by with like a number 4, maybe a 4-aught cable. So you can get by with a single one. So these short circuit tests or load loss tests are always performed on the high voltage winding. You put the equipment on that side and you short out the low side. So that's the full load test. How do you think you would measure or solve for RC and JXM? Remember, make them important. Ramp up the voltage and then do what with the current? Yeah, make the current so small that the voltage drop that we have across RE and JXE is negligible, and take the voltage as high as possible. What kind of a configuration would give you a high voltage and no current? An open circuit test. So my open circuit or no load, sometimes this is called load loss too, is it going to give us the RE and the JXM? So what we have is we apply a voltage. This voltage is the rated voltage of the machine because I'm trying to get what the eddy currents would be at their maximum. So usually that's at its nominal voltages. And the same thing with magnetizing. I'm trying to get as much magnetizing so I can make sure my equivalent model covers all the same. So this is V rated. And the current here is not 0. It's open circuited current. It's as little current as necessary. So the secondary side is run with an open circuit. So all the current that you have should be heading in that direction. You measure I open circuit, V open circuit, and don't forget about P open circuit because you're going to have to build another power triangle. Now, this is just a suggestion. You can do it this way or not. But when elements are in parallel, we just got done doing a section on building Y-bus. And remember how we worked with admittances? It's usually easier to solve for Y, which is equal to I over V. And this is an angle of theta. That's an angle of 0. And that's going to be equal to 1 over RC plus 1 over JXM. So if you solve for I divided by V, you're gonna get the admittance, and then you just say the real part, 1 over the real part is R sub C, and 1 over the imaginary part is X sub M. So don't calculate the Z term, calculate the admittance term. Solve for that. And that's how you can get these tests. And this is real world. I'll show you how real world it is. Oops, I guess I don't have that up. So here is a transformer test report for a transformer that's just up the road here in Pasadumke. There's a wind farm there, not a huge one. But here's a transformer test report. And you can see that we have no load losses and load losses, right? And for your next homework assignment, I would like you to tell me what the equivalent circuit is of this particular transformer. Doable? It's only a 99-page document. You can figure that out, right? In your spare time. Yes, no? You have all the tests you need to be able to calculate the equivalent circuits. So I'll post that at the end of class. That can be your next homework assignment. Tell me what the equivalent circuit model is. Just on the one side of the transformer, you can pick if you want it on the high side, voltage side or the low voltage side, but I only need to see 4 elements. I don't need to see 6 elements. And you should be able to parse through this document and figure out the test information or the test parameter that you need. And it is all in there. You actually have the information that you need to be able to calculate that. Okay, I'll put this test report up there, and then I'll ask you to go ahead and basically do this. Just one problem for your next test, homework. How's that? Very magnanimous. Any questions on that? Doable? Nobody's nervous? You want some hints? Way to start? So what did I call the tests? I call them open short circuit. Did you notice I tried to use different terminology? What did I call the other tests? I called them load loss and no load test. I wonder, in the table of contents, do you perhaps see those terms? So maybe instead of going through the entire 99 pages, I might focus in on the tests that are actually done that we just talked about, right? The load loss and the no load. And so taking a look at those may give you a lot less stuff to filter through. Okay. But for these other pages, they are really useful parameters, like the technical characteristics. If you want to learn a little bit about the transformer, this tells you what the details are for the transformer. So it's got some pretty good stuff identified in here. Okay. Tells you it's a 60, 80, 100 MVA. One of the things about transformers, especially oil-filled transformers, if it's just sitting there, you can see there are fins on it, and that's to help with, dumping heat out to the environment. Over here, in a transformer this size, they need a lot of help to do it. So the reason why it has 60 is what's called its base rating. 60 is what it can do if it's just an ambient, and the ambient temperature is like 90 degrees. That's how much MVA you can run through it before you can start causing problems. To go up to 80, you've got fans with radiators on the outside, and the fans are moving air. So you're not just getting convection or conduction cooling, you're actually getting forced air cooling across the fans, and that cools the oil much more. So you can run it to 80 MVA. 100 MVA means you've turned on your second stages of fans. And so it really is temperature dependent, because in Maine, right? How often is it going to be like a 94, was it 30 degrees C? I think is around 94 degrees. So how often is it going to be 90 degrees around the transformer? Probably not all that often. And in the winter, it's going to be 30 degrees, right? So in the winter, you can push these things much higher than 60 MVA. You can run it at 80 MVA without any fans. There is a temperature measuring device that helps to measure that and turns those on and off. Some other helpful things that you might want to know is the technical characteristics. You will note there's a high voltage winding and a low voltage winding. Remember we talked about primary and secondary? They don't even identify it here. The transformer manufacturer, in this case is Siemens, they're telling you the high voltage winding, because you can run it either way, is rated at 115 kV. And the low voltage winding is rated at 35,000 volts. Remember how we talked about the short circuit, the load loss test? Where did you apply the test equipment on? Was it the high voltage winding or the low voltage winding? Who says high voltage? 3 people, 4 people? Who says low voltage? Who's not sure? Remember, you want to do it on the winding that has the smaller current, right? Because the voltage is going to be lower as it is. So I'm going to run it and set up my test equipment to use the smallest cables that I can possible. So if I'm running it under load conditions, which means I'm running it at full load, which winding is going to have lower current draws? The high voltage or the low voltage? The high voltage, right? Because of that constant power thing. So the load loss test, the test equipment is applied on the high voltage winding. Let's go back to the no load test, which is the open circuit test. So you're running the one of the windings with no load on it, it's completely hanging open. The other one, which would it be easier to test? To put rated voltage at 115 or at 34.5? Not a trick question. The other test, the short circuit or the open circuit or the no load test. Do you apply all the test equipment to the 115 side or the 34 side? 34.5 side? 34. Why?
I don't quite remember. I'm sure like what you said was talked about students.
It's kind of that way, but do you think it's easier to buy a power supply that can put out 115,000 volts or 34,500 volts? The lower one for sure. I'm not saying it's easy, but if you got to go out and buy a power supply that can put 115,000 volts and then run the cables and all that stuff and need different insulation, it's much, much, much harder to find a 115 kV power supply than it is 34.5. So when you're looking at your data, here's the key thing. This right here is going to have the load loss test. And this is going to be the no load test. So you have to make sure that you're going to reflect the impedances to the same side, either the high voltage side or the low voltage side when you do this work. Okay. And there's some other things when you look at the test reports, you'll see some different data. If you think about it and you come up with a reasonable assumption, I'll probably be okay, but there's one very obvious one. What I'm trying to do is give you a lot of practical, like why you do things. And this is, again, exactly how all these devices are tested. You'll even see that in this test report, how they do it exactly the way we talk about in class, just because practically it's much harder to do things the other way around. Yeah, I can find 2000 amp cables, but I'm paying a lot of money for that. Or I can buy 200 amp cables and spend way less money. I can buy a 115,000 volt power supply, but that's a lot more money. And talk about a risk, you know, I've got 115,000 volts. That can arc across a lot more. I need special protective equipment. I need special meters. I need a bunch of special stuff. 35 kV is a lot more readily accessible. I'm not saying it's easy, but The lower the voltage, the safer it is, the easier it is. So run your tests on the low voltage stuff if you can. All right, did I give you enough information to start to tackle the problem? Okay. I'll make that due that a week from today. Good. You have one homework due on Thursday and then that one will be Tuesday. Here's an example so you can see some of the work yourself. The open circuit, and I'm harping on this to kind of help you with your homework a little bit. The open circuit or the no load test, using terminology there. You've got 20 amps with 10 kilowatts of losses. So I'm giving you I, and I'm giving you P, right? But I forgot to give you V, correct? Not correct? I gave you V because the open circuit test means run it at rated voltage. So you're either going to use 200 kV or 80 kV. Right? It's just going to be one of those parameters. So you do have the voltage. You just have to pick which one of those two. Same thing with a short circuit test. I didn't tell you the current because you should be able to calculate it based on the nameplate of the transformer. 100 kV, 200 or 100 kVA, 100 MVA, sorry, and the voltages are 280 kV. It does matter. Use the convention that we talked about. Okay. So you do have the ability to get V open circuit, and you do have the ability to get I short circuit, or V full load and I load loss. Okay. So here's the value where we're doing the short circuit test. You can see that we calculated on the high voltage winding. You see it's 200 kV, right? So we connected and measured on the high voltage side because it's using 200 kV. So we get 60 ohms. We do our calculation. And you can use I squared R if you want to do it that way, or you can do the approach where you're solving for Z equals RE plus JXE. It doesn't matter. But I solved 2 ohms here, and then XE is almost the 60, right? Because the 2 is so much smaller than the 60 ohms. You just call it 60. Close enough. For the open circuit test, I did just the 200 kV here just to see you can do it. But realistically, in the real world, you'd be doing it on the 80 kV side. So I've got, excuse me, I've got V squared over my P, which gives me my R, 4 mega ohms. And then to solve for the parallel combination, my XM gives me 10,000 ohms of values. And you will note these values here are way smaller than these values here, which is what it should be. You should always have very small values for RE and JXE in comparison to your RC and XM. If they're big, then that means you're going to have a pretty lossy transformer, and it's not going to be a very productive or a very efficient transformer. So this is the last topic of our transformers for residents. Remember we talked about what goes in your house? So in your house, you just have a single phase transformer, and you can pick any phase you want, or you can pick any 2 phases. Most of the transformers that you'll see, they'll be single phase from phase to neutral, but sometimes you run them across 2 phases if you want. You just have to change the primary rating of the machine. I mean, the primary voltage of the transformer. So you can see this one's connected phase C to neutral. And I have a single winding that I split in the middle. This is still one winding, but I'm just pulling out of the center of those 2 and giving it my center tap. And then I take my center tap, I run that to ground, and I've got my plus 120 here, plus 120 there. It's still 240, but going across the neutral, which is what you have for your plugs, that's at the center position of the transformer. And the voltage is at 0 volts because I've connected it to ground. Okay? That has to be connected to ground. It shows these going over here to earth ground. So for true electrical isolation, you would not want to have that connected to ground. But from an electrical safety perspective, we can't have that, right? So we have to ground everything as much as we can so that devices will have faults and then they'll be able to be detected that there's a fault that occurs. So you do have to show the grounds. But if this wasn't here, if I have a fault from here to here, no current flows through there because it's an insulator, right? It's all just flowing through the magnetics. There's no physical or electrical connection between the primary and the secondary. So there's no short that occurs. All right. Everybody knows what they're doing with their homework? Again, this is the time to ask because it can be overwhelming to do this problem if you don't have a couple clues of where to start. But what I'm trying to do is, and again, this is where there's some differentiation for the EET program. We try to do as many we can real world applications. And so what I'm trying to do is give you a real world application, which will take you a little bit of time to sort through the data. But I've given you hopefully enough clues here that you can say, all right, I can really focus on the needed pages. There's only a couple pages you need to focus on. And then you can pull out whatever necessary information you need. Questions on that? If you know what you're looking for and you know the parameters to use, it's probably going to be 5 or 10 minutes to do this problem. I will say, and I forgot to add one thing, this is a 3-phase transformer, right? With voltages that are line voltages and phase voltages. So be careful when you look at 115 and 34.5, you got to think about, are those line voltages and or phase voltages? And you can tell a little bit, see the connection here? This says it's a Y connection, and that's a delta connection. So this transformer on the high side is connected like this, and on the low side, it's connected like that. So if you're trying to solve for the impedance of one winding, you've got to make sure that you're using a phase to neutral voltage on the high voltage winding. On the low voltage winding, it's the same, right? But on the high voltage winding, you just have to be a little bit careful. Same thing for the current, right? We know that the current, that line and the phase current are the same, but over here, this current is not the same as that current, right? We know that from KCL. So we have to be a little bit careful about doing those. So just be mindful you're working with 3-phase and you have line and phase quantities, you have to tease it. So I apologize for not saying that earlier, but I want to make sure that you understand some of that stuff. Okay. Anything else? Got like 9 minutes left. I know I started a couple minutes early, but any questions on the homework that's due on Thursday? Building some Y-bus stuff, right? Doing some simple circuit analysis. Yes, sir. A couple, 2-3 pages should be plenty with your results. Again, it doesn't have to be a book. It's just explain it to yourself. And if you need a book to explain to yourself, that means that you probably don't understand it. Brevity is key, right? We're trying to be a technical writer, which means short, succinct, to the point. Technical writing, and my wife tells me this all the time, when I write stuff, it comes across as very rude because it's very curt and very, hey, here's what it is. And the reason why you don't want to get into a lot of additional discussion when you're doing technical documents is because it's confusing. If I have to read 7 paragraphs to get to this one point, I've forgotten some of the stuff I've read in my first paragraph. So if I can condense all that information into one paragraph, then it means that I can usually grasp that information better. So, I mean, I have written 70-page, 80-page documents, but I was conveying a lot of different information. But if you are looking to, be really successful in your careers, being able to write efficiently is a really important skill. That's probably the most important skill that I have out of all my stuff. I mean, obviously you have to have some technical ability, but because I can write reasonably well, it's resulted in a lot of people still wanting to have me do stuff for them because they can give me an assignment and I can respond and write usually pretty quickly. And it's gotten to the point where I've done enough practice that I actually enjoy writing. I don't mind, like people, most of you all, when you have to write a report or a technical paper, it's like, oh no, really? I've got to do this? But as you evolve through your careers, it hopefully will transition to like, hey, I don't mind doing this so much because that is such an important skill. Effective communication, not just everybody can speak relatively well, but actually being able to write cohesively, efficiently is a really big skill. Okay. I'll give you one hint. Don't put any acronyms that I don't want to see LMFAO in your reports. It's not what I would consider professional. Yeah. No thumbs up emojis or whatever. Those don't really translate all that well in technical documents. They leave a lot of room for interpretation. And so even think about that for email correspondence, because you never know, those things never disappear. And so if you use things that people are struggling, like, I don't know if this is professional or not. You know, that's one of the things you got to think about. Okay. Any questions? How about TV land? Any questions in TV land? Going once, twice, get some thumbs up. Okay. All right, I'll let you out a few minutes early. Have a wonderful afternoon. And I will see you all on Thursday. Take care, everyone.
See you, Paul.
Thanks, Mason.